Good morning, everyone. We are going to start our next topic, that is solid state physics. We just studied about solid state physics in the previous classes. Now, we are going to learn about this solid state physics. Now, we just started with the solid state physics. We had an introduction. What is the aim of solid state physics and what is solid state physics and why we start up with the solid state physics and what is the content that we are going to learn in this solid state physics class. So now what is our aim? In the previous class we just started with our aim of solid state physics and what is crystalline solids and what is actually the meaning of solid state physics and what is the main importance, what is the point in studying about solid state physics for an engineering students. As an engineering student, why you need to study about solid state physics. And then we just come across the applied physics and solid state physics. They are the same, what you can say, faces of the coins. And we just have a glance. We had a glance about electrical resistivity of three states of matter and how this matter classification has been varied with respect to the temperature. So that is metal or insulator or the superconductors. Now we just had a glance of it, and here also the next slide. You have seen that the difference about the temperature with respect to the different metals, and then we started with the crystal structure. So now here we just in the crystal structure, that is chapter 1, we have to study about the solid materials, that is crystalline, polycrystalline and the amorphous solid, and what is the meaning of crystallography and what is crystal lattice. So that we have already discussed in our previous classes, and what we are doing here is that we just move on to the next one, that is here we just go to the solid state physics, the main topic here. What we are going to learn about this crystallography. Now just a minute. Now we just start with this now see here, the crystallography is a branch of science that deals with the geometrical description of the crystals and their internal arrangement. So now just we move on to the next slide. So what is that elementary crystallography? You can just have, we should have a basic knowledge of crystallography. Is essential for solid state physicist, and also it is very, very important for an engineering student. Now what we are going to do here is the next in the next class, in this class, that is our whatever the discussion we have done, that is up to the elementary crystallography. Now we just start with our assumptions of crystal lattice. What is actually the meaning of crystal lattice? So you can just see that crystal lattice is nothing but an infinite array. Here we just had the crystal lattice. What is crystal lattice here? See here, we cannot study three-dimensional object or particles, right? So we have to imagine some two-dimension aspect here. So what we are doing here is that we are starting with the assumption of the study of the arrangement of the atoms, how the atoms are arranged in the solid. So here what we have done is that we have taken an imaginary points. You can just see these imaginary points, right? So these imaginary points are nothing but, we have just mentioned that imaginary points. We start from this reference point, that is O, and we are having a point A here. Let us consider that point B, C, D, E, and so on, right? This is continuous process. So what we have done is that just we have taken the length of OA as small a and the length of OB as small b, and definitely whenever we draw some two lines, we will have we will have some angle, right? So whenever you want to take an imaginary line segments, you definitely will have an here an angle. So let us consider that angle is represented by alpha. Now one thing that you have to remember is that what is actually the infinite array of points? Infinite array means the points here are arranged in infinite number of times. You see, these points are continuing, these points are continuing, this point is continuing, and these points are continuing. So we just call that as infinite array of points in space. Why we'll call this array? Array is nothing but they have been arranged in a systematic order. So here each point is identical to its surrounding. When you consider, let us consider the point C. So when you consider this point C, this point C is identical with the point B, and this point C is identical to the point D, and point C is identical to point A, right? Like this, three-dimensionally, the property of the point C is exhibited by all the other points, or we can say the neighboring points. So each point has an identical surroundings to all other. So these arrays are arranged exactly in a periodic manner. We say that these arrays are arranged exactly in a periodic manner. So now what we are doing here is that we just start our discussion. So what is actually the meaning of crystal lattice? So crystal lattice is nothing but, crystal lattice define an imaginary arrangement of points, right? So an imaginary array of points is nothing but lattice, and since we are talking about crystalline solid, so we just call that as crystalline solids. Now what you can say here is that second aspect that we are going to learn here, what is actually the meaning of crystal structure. So crystal structure can be obtained by what you can say by resembling. See, these are the points what we have discussed in the previous C. This A, B, C, D, E, and O, A, and so on. These points I have taken in the second slide. You can just see these points are, let us consider this is O, A, B, C, D, E, F, G, H. Now what we are doing, if this crystal lattice, you can just see, this crystal lattice is added with or associated with the atoms or molecules, then whatever the image that you are getting here is equal to, you can just see that is equal to. So whatever the points, what you are getting here is nothing but these, the pattern is known as crystal structure. So what will be the ultimate definition of crystal structure? So crystal structure can be obtained by attaching the atoms, a group of atoms or molecules or ions, which are called bases. The other name of basis is nothing but motif. So to this lattice sides of the lattice point. So now see, this is the what you can say a general definition of crystal structure. So directly what you can say that crystal structure can be obtained by associating the atoms or molecules or identical or ions, right? So when you associate this crystal lattice with the constituent particles, so whatever the pattern that you are going to obtain, that pattern is nothing but we'll call that pattern as basis. You can just, we go to the next one. Now we can have a two-dimensional, see, these lattices are nothing but we'll just call that lattices. The name, this particular assumption of lattices was given by Bravais, scientist Bravais. So we just have a glance of it, the two-dimension Bravais lattices with different choices for the basis. What is the meaning of different choices of basis? So now you can just have the arrangement of the lattice in the different patterns. You will have different, the arrangement will differ. You can just arrange the points in different orders such that the environment about each point will be the identical or will be same. So Bravais lattice or crystal lattice, here, why we Bravais lattice, I am telling that these lattice assumption is given by Bravais, so therefore we will call this as Bravais lattices. So these Bravais lattice is combined with the basis. Now what is the meaning of basis? Simply basis means the association of atoms, molecules or ions, or else we just call that as constituent particles, and whatever the thing that we are going to obtain here, that is nothing but crystal structure. Now you can just see, you can just imagine, so what is happening here in this particular slide. You can just see here. So what is the meaning of crystal lattice here? Again, if I move to the next one. So what is actually the meaning of Bravais lattice? For your convenience, what we'll do is that we'll have more discussion on basis. So a group of atoms which are describing the crystal structure, so we'll call such thing as the basis. Now you can just see here. Now here we have taken again the same reference point is O, A, B, C, right? Now O, A, B, C, you can imagine that this is the pattern which has been obtained by joining these points. See, O, A, B, C, D, E, F, G, H. So now this particular pattern you can find a different pattern also you can find by joining the different points. See here, I can join these different points like this. You can just see my arrow. See, this point can be joined in this particular fashion also, right? In this particular fashion also. So you'll get the same, you'll have an identical, what you can say, property with respect to the reference point, whatever you have taken. Here the reference point is O. You can just take the reference point here, a different reference point. So whatever the image or the pattern or the geometrical figure you'll get, that geometrical figure will give you the information regarding the structure of crystal. See, this is schematically just imaginary. Since it is an imaginary, you can just have this discrete arrangement of the what you can say points, and here the periodic arrangement of these what you can say this particular colored points, which resembles that they are periodic in nature. So here the situation, what the first figure says, that this first figure is nothing but this is the case for an hexagonal crystal. No, sir, what is, we are directly starting the topic hexagons, or you have not started with this. So this is only an example which is given to you. So how the lattice points are arranged for a given crystal. So here crystal lattice obtained by identifying all the atoms. You can just identify, see, these are atoms. Now these are atoms, right? So here the colored picture, whatever you are observing, these are nothing but these are the atoms. Now you can just go for the next one. So here, now we can just see the crystal structure. See, you can just see, you will have a small spear-like shape that is blue, and also you are having an orange, right? Here, see, you can just see how they are identical to each other. So these are identical to each other. Now we are not mixing the atoms with the lattice point. You can just see here. So let us consider this. This is lattice point, and this is your atom. We have just shown that how we can associate the lattice point with respect to the atoms. So lattice points are infinitesimally points in the space, infinitesimal points, very small points, and they are arranged in a infinite manner. So lattice points do not necessarily lie at the center of the atom. So here, let us consider these points are not exactly at the center of the atom, right? So here, this is only the simple structure of the, what you can say, as a face of the solid, particular face of the solid, which indicates that how these lattice points are arranged. This is only a schematic diagram which shows that how you can know the crystal structure, right, in an imaginary level. So here crystal structure is nothing but again the same thing, crystal lattice. Here I said that the blue spheres are, let us consider that are crystal lattices. If I associate that crystal lattice with the atoms or molecules, you can just see here, the blue one is crystal lattice, and here the orange is nothing but atoms, molecules, or ions. So now this is nothing but as what you can say, this is a schematic observation of the crystal structure. Now we'll go to the next one. So as you go to the next one, what is actually crystal lattice has been classified into. Here the crystal lattice has been classified into two different classifications are there. Here you'll find that here, see here, Bravais lattice crystal lattice is actually is been given, the concept of this is given by Bravais. So I just remove, see here, we are removing this particular word crystal, and instead of that I'm just writing it at Bravais. You can just see. So these crystal lattice or Bravais lattice have been classified depending upon the arrangement of the lattice points or the atoms. They have been classified in two categories, that are Bravais lattices and non-Bravais lattices. So here the Bravais lattices and non-Bravais lattices. Here what is Bravais lattice? Here we already told you that all the atoms or molecules or the ions are same kind, and the lattice points are equivalent to the atoms. Now this is called Bravais lattice. And what is non-Bravais lattice? Atoms can be different kinds. Some lattice points are not equivalent, and a combination of two or more Bravais lattices. So this is called non-Bravais lattices. So here non-Bravais lattices. So sir, we haven't understood what you are going. See, what we are doing here is that we are, see, directly we cannot see the atoms which are residing in the solid. So first of all, we are assuming that how the atoms or molecules or the ions are what you can say, are arranged. So let us consider in two-dimensionally how they are arranged. Let us consider like this. So let us consider these are nothing but these are the arrangement of the atoms, molecules, or the ions. So we just see whenever we talk about some assumption, so what you go for an ideal thing. So what will be the ideal thing? The ideal thing is nothing but it's a one by one. So ideally we think that everything, whatever we think that we think in an ideal manner. So in ideal manner, you can just see the distances about each point. See, for an ideal thing, the atoms arrangement are nothing but they are equidistant with each other. You can just see this is one atom, second one, third one, fourth one, and so on. So here, first of all, we just see if this is the arrangement, we'll call such arrangement as nothing but the atoms are same kind, and all the lattice points are equivalent to each other. So here, what is non-Bravais lattices? Now this will be not this case is not what you can say valid for every solid material. So there may be some different aspect also. Here also you can just see the atoms can be different kind. Here you can just imagine, see here. So these are the atoms are arranged in ideal manner. Again, there is a possibility that you may have another lattice point, which is lattice point or atoms, which are not in a periodic manner. See, atoms can be different kind. Some lattice points are not equivalent, and these combination of two or more, we can say this is nothing but this arrangement, we'll call that as the arrangement of these lattices or the atoms that come under the category of non-Bravais lattices. So okay, so now this is the assumption that you have made. So now we just have a depth understanding what is the different types of the crystal lattices. So here the Bravais lattices and infinite. See, again I say infinite array. Why I am saying infinite array again and again? I am telling you infinite array. So infinite array means, see, whatever the thing that you are going to study, that is about 3 dimensional. So let us consider, see, atomic level is right. I'm talking about a dimension of 10 to the power of minus 10 meters, right? So now we have just taken an example of niobium film here. So for your understanding purpose, we have taken a film image or schematic image of the niobium material, and see, you can just see the arrangement of the atoms. This is a microscopic image. Whatever the image you are seeing, see imaginary points, whatever we have seen, the same thing, it look like same thing here. See here, Bravais lattice is an infinite array of discrete points with an arrangement and the orientation that appears exactly the same from whichever the points the array may be viewed. So if you can see the angle from where you are going to array, you can just see that angle may be varying, but here the orientation of these atoms or molecules or the ions will be identical to each other. For that reason, we have just taken an arrow mark here. You can just see this arrow mark, and this is a reference point. This is reference point, and here you will find that this arrow mark. So this is the reference point, and this particular array, or whatever this, you can see the arrow. So this particular arrow indicates that the identical nature of these particular points, and we call such identical arrangement. See, again, now this is the microscopic image. Now what we have taken, we have taken in some imaginary points here, and see these particular, what you can say, this is a square, and this square can be can be drawn from any, you just take any 4 points. See, if you take any 4 points of this particular diagram, so you will get an what you can say, the square structure. So here we'll move to the next one. So the different, so we just studied about the Bravais lattices. Now what is non-Bravais lattices? See, not only the arrangement but also the orientation. So what is the orientation? Means the direction. You will find that the atoms, the arrangement of the atoms will not be in a perfect periodic manner, but that arrangement or the what you can say, the direction of the atoms, arrangement of the atoms are nothing but we'll just call it as orientation. So orientation must be same from every point in a Bravais lattice. Now here, for that, for understanding this non-Bravais lattices, now I think that you had a very good understanding what is actually the meaning of Bravais lattices. Now what is the non-Bravais lattice? Here you can just see that non-Bravais lattice is nothing but the arrangement. See, not only the arrangement but also the orientation must appear be exactly same from every point. So if I say the only arrangement, no. Arrangement with respect to the arrangement, you should have an exact orientation of the atoms should also be identical with respect to the arrangement of the points. Now here, so for your understanding purpose, we just I have taken some point here. So the red side has a neighbor. See, you can just see, yeah, this is what, this color is what? Red, right? And we just, what you can have, you are having color blue. So now, the red side has a neighbor to an immediate left. You can, if you just see here, the blue one instead has a neighbor to its right. So blue one is having neighbor to the right, and the, what you can say, the red one is having immediate to the left, right? And the red and blue sides are equivalent and have the same appearance. You can see there, the red color and the blue color, the appearance of the pattern, appearance or the pattern, whatever you are observing, have the same appearance. Red and blue sides are not equivalent, but the same appearance can be obtained by rotating this. So you can just, we have taken an example of honeycomb in order to understand what is the, what you can say, how to tell you about the definition of non-Bravais lattices. So let us see, the when you see a honeycomb, so what you will observe, that you will observe this particular pattern. So I have taken a reference point here. So here red and blue sides are equivalent and have the same appearance. So here the appearance is same, but the sides are not equal to each other. This side is different and this side is different. So this particular structure you will observe if you rotate this particular reference point, whatever the reference point you have taken, 180 degrees. So now this is only for your understanding. See, in the examination point of view, or with respect to the what you can, the syllabus, we will not ask you this particular concept, but this is for your understanding purpose. Now, so again, see here, whenever I talk an imaginary thing, so then that it should be verified mathematically. So whatever the statement we are going to tell here, that statement should be verified mathematically. So how you are going to verify that thing as a mathematically? See, now a space lattice says, so see, for that instant what we are doing is that, so let us consider here, you can just see the figure, origin, again I am considering this as an origin, and this is point A, and this is the point B, right, with respect to this particular, see, reference point is this, and you just take this one, small a, the dimension is small a, here the small dimension is small b. So you can just see here, a space lattice is a set of points such as a translation. When I say translation, what is translation actually? Repeating the function, a particular parameter or a function to infinite number of times such that the environment will not change. So they are identical. That particular repetition will be identical. So such a movement or such property is known as translation property from any point in the lattice by vector. So this can be represented by Rn is equal to, see, this is the resultant, or if I say resultant, right, Rn is equal to n1a plus n2b. So locates the exactly equivalent point. We want to know what is the equivalent point here mathematically. So now the point with the same environment as P. Where is the P here? You can just see. Here there is a point P. Now this is a translation symmetry. The vectors A and B are known as, these vectors A and B, small, you can just see A and this is what B, are known as lattice vector, and N1 and N2 are nothing but they are integers. Why we have taken integers here? Why cannot we take a whole number or a natural number? So why we have taken integer means whenever you take a reference, if I take a reference point here C, so to the left hand side I definitely will have a negative value. To the right hand side you will have a positive value. If I take a reference here, so again, this left hand side you will have a negative value and this right hand side you will have a negative positive value. So definitely you cannot take a whole number or a natural number. So we have taken, that is the reason that we have taken the pair of integers which are having the value, and these values are dependent upon the lattice point. So for that reason we have just taken, see here, the point D. Where is the point D here? See, you can imagine point D. When I say point D with respect to the origin, so this is called, when you take a graph paper, right? You take a graph paper, this particular length will be 1 and this particular length will be here 2. So I have to just see here 0, 2. Your x-axis, you are exactly at 0. So your coordinate, what you can say, x coordinate is 0 here. Why? Because we have taken a reference point origin. And your y coordinate, the length from here to here, you can just see the graph also. You'll find that point is 2. Now, where actually you are seeing. Now this is the reference point you have taken. Again, see, this is the origin. So definitely below the origin, we have taken a point F. So definitely this will be 1. See again, at the Z you will have a 0, we have taken an origin. So x-axis 0, and this indicate y-axis in the negative direction. So that will be the point 1, that is, we have taken 0, minus 1. Now I think that you got an idea why we have taken integers. So here the crystal lattice can be mathematically defined with 2 dimension, with Rn is equal to n1 a bar plus n2 b bar. Now this is a 2 vectors a and b from a set of lattice vectors for the lattice. So what it means, the same thing what we have come across. See, we have taken here D as a reference point. You can have an arrow here, right? And you can have a same figure, you can just have this is vector A and this is vector B. This is only for your understanding purpose. Now we'll move to the next one. So 3-dimensionally. See, this particular figure, I'm talking about lattice vectors 2-dimensionally. So what will happen with the 3-dimension? So when I take a 3-dimensional, if I join the points 3-dimensionally, definitely you will get a cube here. You can just imagine that this particular type is nothing but it is a cube. So here you will find that there is a cube here. So if I just join that 3-dimensionally, that figure is nothing but cube. And you will see here, pertaining these particular angles, definitely, so I am talking about x-axis, y-axis and z-axis. When I talk about x and y and z-axis, you'll have an angle. And that angles we have just taken as alpha, beta and gamma with respect to 3 coordinate axes. That is x-axis, y-axis and z-axis. So here, we have not taken that as a t. Here we have just taken r prime is equal to r plus ua plus vb plus wc. What is this, sir? So let us consider this is, see, you will understand this particular aspect from, you can just see here, from the figure, you can just see the figure. You just take a point P here, and these are the points A bar, B bar and C bar. So ideal 3-dimensional crystal is described by 3 fundamental translation vectors that are A, B and C. And if there is a lattice point representing by the position vector small r, see that this lattice point is representing the position vector small r. So this small r is nothing but it is a position vector small r. And these all lattice points are represented by the position vectors. So you'll see when you talk about 3-dimensional, so we just take 3 position vectors u, v and w. So these are nothing but, here we'll call that as an arbitrary integers. Arbitrary means some that has particular constant value, some constant value. See, so in 2-dimension, we just in the previous figure we just had lattice vectors 2-dimensionally. In this one we had a 3-dimension, we'll have a lattice point 3-dimensionally. How the lattice points are arranged and what will be the figure or the pattern that you are going to observe. So how many Bravais lattices can be what you can impinge in 2-dimension? See here, you can have the lattice point arrangement such that the environment about each point is identical with respect to the neighboring atom. So how we can arrange the lattice point? You can see here, rectangular, general, this is a general one, rectangular part, central rectangular, square shaped lattice point and hexagonal. So 1, 2, 3, 4 and 5. So we can arrange the lattice point in this 5 particular orientation such that the environment with respect to the neighboring atom, you can just take this as a reference point, and environment about each point will be identical for these 5 different pattern that you are going to that you are seeing actually. So now this is called 2-dimensional Bravais lattices. Now when we go for the what you can say unit cell. What is a unit cell here? A unit cell, what is unit cell? A smallest geometrical figure. When you we talk about first of all 3-dimension, 2-dimension. The smallest component of the crystal which stacked together, which combined with each other, a pure translation repetition, they produce a whole crystal. So in 2-dimensional, when you see the 2-dimension structure, when we see a 2-dimensional structure, so these 2-dimensional structure, you'll find that they are stacked with each other. We have shown it this particular pattern, A and B bar. In the previous figure also we had this particular discussion. And here, this is the smallest geometrical figure that we are observed in 2-dimension. So what is happening to 3-dimension? See, unit cell in 2-dimension. See, smallest component of the crystal will stack with a pure translation repetition. So now we just taken a NaCl crystal. Everybody is familiar with NaCl crystal. So we define lattice point, these points are identical, they are having identical environment. See again, we have taken a orange and the blue one. So here, the orange and blue one indicates one is lattice point and associated with C atom. So we'll call such structure as your choice of the origin. Here we can just see this particular, which particular point you take an origin or reference point. So it is your choice. See in 2 dimension, when you join this particular point, we'll call such thing as the unit cell in 2 dimension. So here, we just move to the next aspect. So it may be, we talk about sodium or what you can say, we just talk about the chloride. So whatever it may be, the structure in 2 dimension unit cell will be like this. Unit cell is nothing but it is the smallest geometrical figure which is obtained. Either it may be 2 dimension or 3 dimension. So here we just got for 2 dimension. So what will happen to 3 dimension? You can just see. So unit cell with respect to 3 dimension will look like this in this particular figure. You'll find that this is the shape of unit cell. So one, we define what is actually the meaning of unit cell. The unit cell is nothing but, we can make a note of it. So the unit cell is nothing but it is smallest geometrical figure, right? The smallest geometrical figure is nothing but we'll call that as unit cell. Either it may be in 2 dimension or either it may be 2 dimension. Now, see, you can just see there is a crystal here. You click here, we just start with atoms here, right? So you can see, I talk about basis. So atoms are there. And again, these atoms are combined to form a molecule. And the molecule or the atoms or the ions are arranged in this particular fashion. I join these particular molecules or the atoms or the ion. So I get this particular figure. And when you join these particular figures, it will look like in this particular fashion. This is called collection of unit cell. And these collection of unit cell ultimately result in the crystal. So now this is the, what you can say, one way of understanding how the unit cell has been produced, or the, what you can say, how it is made up of. So now here there are 3 different, for 3 dimensional you'll find that unit cell, what we are going to discuss in our engineering, for engineering purposes, we are very much concerned with the 3 common unit cell which is resembling to the cubic crystal. So you'll find that the unit cell are having different forms. Your unit cell will have different forms. This is one type of unit cell in 3 dimension. This is second type of unit cell, and this is the third type of unit cell that you are going to understand in the engineering. And particularly, we just talk about the cube. This is called cubic actually. This will come under the cubic crystal system. So we'll just have a look of it. There, how the simple cubic, this is called simple cubic. So this is a schematic diagram, and when you see this, we have taken examples of the some spherical balls. So how this simple cubic unit cell look like? You can just see this 2. You can compare this particular thing. These are one and the same. And here you'll find that at each point, at each corner of the unit cell, you'll have the atoms or molecules or the ions arranged. Exactly at the center, you'll find a different another atom which is residing exactly at center. So at the center, we'll just call that as called. That is the reason that it is called body-centered cubic unit cell. See here, there are 3 common unit cell, 3-dimensionally, which is observed in the cubic crystal system. This is called face-centered. This is called face-centered. You can imagine, see here, again, you see the unit cell, how many, what you can say, the atoms or the lattice points there, how many unit cell having 6 faces, right? 1, 2, 3, 4, 5, and 6. So how many atoms are there? Ions or molecules are there? What you can say, 1, 2, 3, 4, 5, 6, 7, 8. This is the case for simple cubic. 1 is increasing in the body center. Here, you'll find at the corners you are having 8. Here, at the corners you are having 8. But exactly at the center of the, what you can say, cubic structure, you'll find one more lattice point. So that is the reason that it is called body-centered. And it has been indicated with the red part. You can see, these are white and this is what? Red one. Here also, there is a red here, and this is what? White. Now, so now this is, we'll call that as primitive and non-unit cell again has been classified in 2 categories. So you have just seen, see here, we have seen that unit cell apart from the corners, this is one more lattice point. Here also you have got a different lattice points here. So this particular thing is very much different. So here, unit cell have been classified into two different categories. That categories is nothing but primitive and the non-primitive unit cell. So now here, these particular aspects that will come to the end of our class, right? So in the next class, we just start with the unit cell and different types of unit cell. So here, what you have to do is that for attendance purpose, what you have to do, you have to again just see the video very carefully and try to give the correct answers such that you can get the attendance depending upon your right answers. So your right answers is directly proportional to your attendance here. So again and again you can just see that that is the reason that is starting classes very less time I have taken. So you can for this is only for what you can say since we have just started the classes. So therefore what we are interested is that we need to make you understand. So wherever you have a problem, so in the next tomorrow class, that is we have a Zoom call. So we'll be sharing you the link, and then you can have whatever the doubts you find in the physics class or whatever see if my voice is low or if I'm getting a bit very fast and if you don't understand any particular topic, since it is only 2 classes, and definitely I will try to make you understand in a very simple manner and try to just solve your problems, what are the problems related to the class, to the subject or the content. So thank you everyone for your patience, and please try to understand it and read it in the class whenever you will get what you can say, whenever there is a class, then only then you will definitely within if you spend some 10 to 15 minutes, so again you will definitely understand it, and if you understand it, definitely you can just solve that 5 multiple choice questions which is given to you. Okay, thank you everyone. We will just end our class today.